Hello ladies and gentlemen, and today I'm going to be introducing episode 4. This one deals with the electron structure, and it's the last video in this group, which gives you an overview of our proposition. In particular in this video we will be showing you where the electrons exist within the atom, at least at 0 Kelvin, i.e. when they're not all moving and bouncing around due to being bombarded with heat. Also we'll be looking at the electron filling pattern, which nature follows, and explaining why it doesn't follow Madelung's rule. Now before we start we need to explain that there are 4 main types of electron shells, which are called S, P, D and F. Each S shell can hold a maximum of 2 electrons, a P shell can hold a maximum of 6 electrons, etc. as shown. Furthermore, each shell can be broken down into 2 rings, and thus each S ring can hold only 1 electron, each P ring can hold a maximum of 3 electrons, etc. Moreover, these shells exist at multiple energy levels, so for example there is an S shell at energy level 1 and another one at energy level 2. Therefore, to distinguish between each of these shells, they are referred to by a number and a letter, where the number represents the energy level and the letter represents the type of shell. Thus, a 1s shell exists at the lowest energy level and holds a maximum of 2 electrons. To make it even more complicated, not all shells exist at any one energy level. For example, energy level 1 only contains an S shell. Lastly, for completeness, we have given in the third point the exact order of all the shells in terms of their energy level. It is this order, generally speaking, that the electrons of an atom fill in. Therefore, if there were only 3 electrons, they would fill the 1s shell and half fill the 2s shell. However, the one important thing to note here about this order is that it does not follow the different energy levels. For example, the 4s shell comes before the 3d shell, and the reasoning why will be explained in a couple of slides' time. Now that we've described the electron shells and their energy levels to you, we can actually start to explain where the electrons exist within the atomic structure. Here we show you a 3-dimensional diagram of the electromagnetic fields produced by the protons and neutrons within the nucleus. The first important thing to note here is the scaling of the diagram, which is 1 to 1 to 1, i.e. it's not been stretched in any of the 3 dimensions. Thus, if we draw a circle around the nucleus, i.e. the blue dot at the centre of the picture, then we can observe that the field lines are further apart at the top and bottom compared to the sides. This implies that a funnel shape exists at the top and bottom, which is closer to the nucleus than the empty ring that exists on the side. In fact, it is within these top and bottom funnels that the electrons exist, because here there are balance points between the attraction and repulsion of the electric and magnetic fields. This is due to the construction of the nucleus, which generally has negative and south fields pointing up and down, whilst the electron thread only contains a negative and north pole. Hence there is an electric repulsion and a magnetic attraction between the two, as well as an overall electric attraction between the protons and the electrons. Here we've blown up the funnel arrangement so that we can better describe where the electrons sit within the funnel, although we must point out that this diagram is not to scale. However, first of all, let me describe all the points of this diagram to you. To start with, the black dot at the bottom of the diagram represents the nucleus, whilst the 2 pink lines represent the outside of the funnel. Next, we have the electron rings, which start with the yellow ring at the bottom. This represents the first or lowest energy level, being the 1s ring. Next up, we have 2 rings, which represent the second energy level, and which has the 2s and 2p ring, with the s being the smaller of the 2, since it only holds 1 electron as opposed to 3 within the p ring. After that comes the third energy level, shown in blue, which has the 3s, 3p and 3d rings, in that order from smallest to largest. Lastly, we have the fourth energy level, shown in black. However, to simplify the diagram, we've only included the 4s ring. In nature, there would also be the 4p, 4d and 4f rings. There are also higher energy level rings, but we've left that off again for simplicity. The next thing to notice is that the rings increase in size as we go up the energy levels, as shown by the sloping back line which just touches the edge of all the S rings. Remember, those are the smallest rings at each level. Secondly, that the 4s ring, shown in black at the top, is actually closer to the nucleus than the 3D ring, the largest blue ring. This is shown by the grey arc, which represents the distance of the 4s ring from the nucleus, and comes inside the distance between the nucleus and the 3D ring, as shown by the black line on the right hand side. It is for this reason, i.e. that the 4s ring is closer to the nucleus than the 3D ring, that explains why the electrons fill the 4s rings before the 3D rings. However, the 4p rings, which are not shown, would be further away from the nucleus and thus are filled after the 3D rings. This would also be true of the 5s and 4D rings, as well as the 6s and 4f rings, for examples. Secondly, we point out that the rings can only exist within the funnel. Therefore, since the 1s ring, shown in yellow, touches the edge of the funnel, this explains why there are no other level 1 rings, as these will be outside the funnel. The same argument holds for a 2D ring, since the 2p ring touches the edge of the funnel. Lastly, I need to point out that these rings do not hold the electrons. They are the electrons. Thus, for example, if a 3D ring does not contain 5 electrons, i.e. its maximum, then it would not be a complete ring. It would just be an arc. This is the end of the video, but this episode does continue in the next part, so I hope that you will actually join us for that. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.